Today we are going to keep talking about kinetics, and in particular we're going to cover mechanism of reaction, molecularity, and intermediate and catalysts. So rate laws allows us to understand the connection between the concentration of the reagents and the rate. So the rate is proportional. There is a direct proportionality between the rate and the concentration of the two reagents. However, this relationship is non-linear because there is an exponent that we indicated here as y and x. And what I was really stressing is that this exponent is not necessarily the coefficient in front of the two species in the balance equation. It could be that sometimes it's the same, but you would never know a priori beforehand if that's the case or not. So in principle, when you're starting to look at a reaction for the first time, you have no clue what x and y are going to be. The only way to determine x and y is to do an experiment. And then you may figure out that maybe x is equal to a, but most of the time is actually going to be different. So why is that? Why is it that wouldn't be so much simpler if we could just use the coefficient as exponent without having to do an experiment? How come that we cannot rely on that? The reason is that the actual those exponents are basically telling us what kind of collision we need to have. And that depends on the mechanism, the actual steps that are determining the reaction to happen. And the balanced equation is just a very short summary of the reaction. It's just telling us where we start and when we arrive, but we don't really know what's happening in between. So to use an analogy, let's imagine to be in an English class and you're talking about Shakespeare and Romeo and Juliet, right? So they could tell you, well, in a nutshell, the summary is that the story goes that Romeo meets Juliet and then they both die. I mean, technically it's correct. It's just a very, very, very succinct summary, right? So that's the balanced equation. Romeo and Juliet met, and the product is they're both dead. It doesn't tell you all the steps in the story. To be able to determine the rate law, we need to know those steps, and that needs the performing an experiment. So a reaction mechanism is normally different from the balance equation in the sense that it's more complicated. There are more steps. It's a sequence of steps in which some bonds are being broken and some are being formed, and maybe in those steps you have temporary compounds that would not appear in the balance equation. They would be intermediate. Intermediate are compounds that you make during the process and then you use them up, so they disappear. So in the net balance they don't show up, but they are there only as intermediate compounds. So if we are able to determine all these elementary steps, then we can define the molecularity of each of them. Molecularity means number of molecules involved in each step. So if I'm asking you what the molecularity is, I want, as an answer, I want a number. If the reaction is the elementary step is unimolecular, it means that there is only one molecule involved in the step. So like, for example, it's a big molecule that's breaking out in two pieces. If the step is bimolecular, there are two molecules that need to collide with each other. If the step is termolecular, there are three molecules that have to collide with each other. So these are very rare because the likelihood of three molecules actually coming together at the very same time in the very same spot are quite small. So you wouldn't even see tetramolecular. That would just be unbelievably rare. So the really important thing that you need to remember is that the rate law cannot be predicted from the overall stoichiometry. In order to do that, you need to perform an experiment. And what the rate law reflects is one specific elementary step. So of all the steps, the only one that's really important to determine the rate law is the slowest one. So this is an example of how molecularity relates to the rate expression. So if the elementary step, so that's one specific step in the reaction, involved only one molecule, we would say that's unimolecular. If it involves two molecules, we would say it's bimolecular. This may be that the two molecules are different or the two molecules are identical. That doesn't make any difference. It's still bimolecular. It just means that in that step, those two molecules need to collide together in order for the reaction to happen. So this, for example, is going to be 3 molecular because it's 2 plus 1. Okay. So consider, for example, this reaction. The scientists did perform some experiments, and they figured out that the most reasonable explanation for this is that there are 3 steps. And those are the 3 steps. So you may see that in the first step, only one of the molecules is involved, even if in the balance equation there is a coefficient of 2, but the first step requires only one molecule. That's breaking down into 2 smaller molecules, of which the first one, NO2, does appear in the balance equation, but the other one, NO3, does not appear in the balance equation. And that's because in the second step is used up. So if you form 1 mole, then you use up 1 mole, the net balance is 0. So there are some molecules there that are appearing and then disappearing. One is NO3. So if we do a balance, right, so we put together those 3 steps, we should get the very same reaction we are considering. What we can do is cancel out everything that appears on both sides. So it's a bit like algebra, like putting together 3 equations. So NO3 that appears in step 1 and disappears in step 2 can be cancelled out. And we call that an intermediate. Intermediates do not appear in the balance equation. So a priori, you would never know they are there. You need to know the mechanism to figure out that there are intermediates. Or, so at monoatomic oxygen that we've learned is not the stable form of oxygen. The stable form of oxygen is O2. So it's quite an unstable molecule. That's also an intermediate because it appears in step 2 and then is used up in step 3. So the net balance is 0. So NO3 is an intermediate, oxygen is an intermediate. So when we put together what's left, we get exactly the same reaction that we were studying. So this tells us that this mechanism is plausible. Just because it's plausible, it doesn't mean that's actually what happens. It has to be plausible. It has to be consistent with the rate law, and then there, you may still need some more experimental corroboration to it. What do we mean that it needs to be compatible with the rate law? So if I would look at the balanced equation, because there is a coefficient of 2 here, right, I might think that the rate law is equal to K times the concentration of this compound elevated to the second power. But as I told you many times, the coefficient is not necessarily the exponent. So by studying it and knowing that there are 3 steps, the step that's going to be the important one, it's the slowest, is what we call the rate limiting step. That will determine the rate law. So what is this rate determining step? Let's try to understand the meaning of this concept with an analogy. When we do fire drills, the point is to check if there is anything that can be improved in order to have, a quick evacuation from the building. So think about all the steps when we were in class, all the different steps we would have to go through in order to exit the building. We would have to get out of the our room where there are two doors, and then we get into the hallway. Then we have to go through the nearest stairway, so there is a door there. That's a little bit larger of the door we have in the classroom, and then we go down the stairways and we get to the very to the zero level. Well, there is one door that's not even that large to get out from the building. That's what we are supposed to do if there is a fire in the building. So what would you think is the bottleneck, right? So we can probably go pretty quickly through the hallway and even through the stairway, but where people get stuck are the doorways because they are narrow. There are only that many people that can go through, and in particularly it's going to be the narrowest of the doors. That's the door to get out of the building. So if we figure out that the time it's taking for us to evacuate is not short enough, and we need to improve that, and someone comes up with the idea of making the hallway larger, that would be a total waste of time, because that's not where we are getting slow. We're already going as fast as we can. The only way to improve would be to make faster the bottleneck of the process. That would be the door downstairs. So the door downstairs is the rate determining step. How much time is going to take us to go through that door is going to determine how much is going to take us to get out of the building. Any change in any other part of the process would not make any difference. Or another example could be when we used to take exams at night and we had 2 hours. And even if 99% of you would be fine after an hour and they leave, and I have just one person who's going to stay there the whole 2 hours, that's the rate determining step for me. I'm going to be there until the last person has left, until the slowest person has left. So how much time is going to take to perform the exam is determined by the slowest step, the slowest student. Let's see an example, right? So we have this reaction that we've seen before, and through an experiment in the lab, we determined that the rate law is this one. So it's first order respect to N2O5. So the order first, right, there is sort of an unwritten exponent of 1 here, does not correspond to the coefficient in front of that molecule. And that's what I always told you. There is no way you can infer the rate law from the balanced equation. You need an experiment. So the experiment tells us, well, guess what? The exponent here it's 1, is first order, is not second order as you would think based on the coefficient, right? So based on this, some scientists come up with a proposed mechanism. So the mechanism needs to make sense. It's not like you can make up a totally, an unsubstantiated mechanism. So what does a mechanism what are the things that make a mechanism making sense? So there are 2 conditions. First of all, when we put together all the steps, we should get the same molecular reaction we started from. So putting everything together, we should get this equation. Second, the mechanism should agree with the rate law as we determine experimentally. So we want to see that the mechanism is in agreement, let's use different color, with this. So how do we proceed? So let's start with point 1, right? So what we can do is to sum up everything that's on the left and on the right of the arrows, like in algebra, and we should end up with the very same equation. Is that true? It is true because we can do simplification like in algebra. If something appears on the left and on the right, we can cancel it out. So there are several molecules for which we can do that. NO2 appears in step 1 and gets used up in step 2. So we can cancel out. Same happens for NO3, so that's also get cancelled out. And that also happens with O. O would be a monoatomic oxygen that we've learned is not stable. The stable form is O2. Remember, have no fear of ice cold beer. So we can simplify that too. So what are those substances that do appear and disappear? Those are called intermediate. They do not appear in the balance equation because they are not reagents, they are not products. They appear in one step and then get used up in the second step. So you have no way to know that they even are involved, that they are even involved, until you deal with the mechanism. Just by looking at the balance equation, you would be totally oblivious of the involvement of those species. So we have satisfied the first requirement. Now let's look at the other one. The mechanism should agree with the rate law. What does that mean? Well, the mechanism doesn't have just to propose steps. It also has to make a guess, an educated guess, on the speed of those steps. So according to this proposal mechanism, step 1 is slow, step 2 is fast, and step 3 is fast. So as we have seen in the analogy of the evacuation of the building, what's really critical is the slow step. The slow step is going to determine the total speed of the process. So it's the rate determining step. So whenever you are solving these exercises, ignore the fast steps and just focus on the slow step. There has to be an agreement between the slow step and the stoichiometry as suggested by the rate law. So if in the rate law I can see that the only species that's important is N2O5 and its first order respect N2O5, then that means that in the slow step there has to be a coefficient of 1 in front of N2O5. That is in fact the case. So now at this point some of you are going to be mad at me because you're going to think, well, you keep telling us those exponents are not the coefficient, and now here you go and you tell us that that's coefficient. So let's be clear here. What I'm telling you is the exponent in the rate law is not the coefficient in the total balance equation, but it is the coefficient in the rate limiting step, the slow step. If you run into a reaction for which there is only one step, so it's an elementary reaction, then that's the few instances in which the exponent also corresponds to the coefficient in the balance equation. But the problem is you never know that ahead of time. You can only know that when you are done with the experiment determining the rate law. So in principle, when you're looking at the balance equation, you do not know the mechanism. So you don't know if there is 1 step, 2 steps, 3 steps, 10 steps. Therefore, you have no information about the rate law. The only way to write the rate law is to perform an experiment. If we are wondering about molecularity, then the first reaction is going to be unimolecular because there is only one molecule involved. The second one is bimolecular because it implies the collision between 2 molecules, NO2 and NO3. The third step is bimolecular too because it's also about the collision between N2O5 and oxygen. So let's have a look at the energy diagram that so far we have been drawing as one hill because, you know, we were simplifying things. What happens if there are multiple steps, how that reflects into the shape of that diagram. So each elementary step is going to have correspond to one hill, right? So if you have 2 elementary steps, like in this case, you are going to have 2 hills. So what you have here are the reagents. What you have here are the products. And what you have here is the intermediate. The slow step is going to be the tallest of the hills because it's the one that has the highest activation energy, right? The activation energy goes from here all the way here. And so being the activation energy larger is going to be the step that proceeds at the slowest speed. because very few molecules will have enough energy to overcome that hill. This step is going to be faster because the activation energy is smaller. So again, only when the reaction consists of just one elementary step, only in that case the rate corresponds to the stoichiometry of the balance equation, because otherwise you need to know which step is the slowest, and that would be the one that determines the rate law. So for example, in this case, if you look at this equation, right, you see that there are two reagents, so you would think that the reaction would be a decent guess. Let's say you would think that this reaction happens because there is a collision between NO2 and CO. Therefore, it should be molecular, and it should be of second order, first order respect to NO2 and first order respect to CO. And then you do the experiment and you figure out that no, the reaction is second order respect to NO2 and is zero order respect to CO. So that shows you that there has to be multiple steps, that is not just one step. There has to be at least two steps, of which you have a slow one where there is NO2 as a reactant, and it's there is a coefficient of 2 in front of NO2. So that could be a plausible mechanism. We have a step 1, that is the slow determining the rate, and in this one we have two molecules of NO2 that needs to collide together. Therefore, for this, the rate law would be proportional to the second power of the concentration of the NO2. And then step 2, being faster, is the one that involves the CO. So the concentration, even if you increase the concentration of the CO, is not going to make anything faster, because this is where the velocity is determined. So that's why it is zero order respect to the concentration of the CO. So let's see an example of potential way to phrase the questions, right? So you are given the rate law. So you have the balanced total equation, and you have the rate law. The rate law is telling you that is first order respect to NO2 and also first order respect to ozone. This despite the fact that there is a coefficient of 2 in front of the nitrogen dioxide. So obviously there are at least two steps. It's not a simple situation where you have only one step. Otherwise, it would be second order respect to NO2. So they have proposed 4 different mechanisms. You need to figure out which one is consistent, is plausible, because the 3 of them are not. Okay. So what you have to look is the fast and slow. So basically, you could almost cancel the fast one, because the fast one is not going to affect the total rate. So you really want to focus on the slow one. And then of the 4 slow one, you want to pick the one in which the stoichiometry is consistent with the rate law. So you have basically a coefficient of 1 here, an exponent of 1 here, an exponent of 1 here. So you want the reaction in which there are only NO2 and NO3 reacting in a 1-to-1 ratio. So NO2 and NO3 with a 1-to-1 ratio is this one. So this doesn't work, this doesn't work, this doesn't work. This would have the right coefficient, but in this mechanism, this one is the fast step. That's not going to work. If B would be the mechanism, it would be second order respect to NO5, right? 1 and 1. So if this would be the mechanism, the rate would be K times NO5 to the second power. That wouldn't really work because NO5 would be an intermediate. I mean, this has several flaws in the design because it doesn't even correspond. If you put these two together, it doesn't correspond to that. So there are other issues, but really the only one that works is C, because then if we put it together, NO3 cancel out with NO3, so you end up with one of this plus one of that. Then you have the second NO2 from here, so you get the two that you need, and then you have N2O5 plus O2, so that would end up 2 NO2 plus O3, and then you get N2O5 plus O2. Now it's time to watch a movie, so you can stop the video here, go get some popcorn, watch your movie. The movie is about catalysts and the chemistry cat joke, and then we can come back and restart from here. So in the movie you've seen an introduction, you've been introduced to catalyst, right? So we've already kind of introduced catalyst. In this picture, this is a diagram of a reaction that happens in one elementary step, and the blue, so this trace, is the one without catalyst. So it's a mechanism that has a very high activation energy. The catalyst provides a different mechanism that has a lower energy, activation energy. You can see that, excuse me, with the catalyst, the activation energy is lower. It's only 260 kilojoules as opposed to 300 kilojoules. The sneezing was not coronavirus, was just allergy. So, there are some things that do not change with the catalyst. In particular, the delta H of the reaction, so the difference between products and reactants, is going to stay the same. That would be 200 minus 75. So actually you would have to go final minus initial. The final is 75, the initial is 200. So the difference is minus 125 kilojoules. Is negative because the reaction is exothermic. Is exothermic because the products have less energy than the reactants. So that delta H is exactly the same regardless if you're using the catalyst or not. The catalyst is not changing the energy stored in the reactants or in the products molecules. It's just changing the way to get from one to the other. Most of the time, the mechanism with the energy, with the catalyst, may look very different from the one with the, let's use a different color here, let's use purple. Can look completely different. So for example, you could have a mechanism where you go through 1, 2, and 3 steps. So how does a catalyst work? There are two main, let's say, typology of catalyst. The one that is shown here is very similar to what happened in the catalytic converter of your muffler. So in this case, the reaction that we are trying to perform is, you see there is a molecule here that has a double bond between two carbons. And then we are not really told what's, on this side of the molecule. So let's imagine there is just, something else. It can be quite a long molecule, but we are only interested into the reaction side for the molecule. So this molecule could be, for example, vegetable oil. Vegetable oils have double bonds between the carbons, and this makes them liquid. And as opposed to animal fats that have very, very similar chemical composition, except there are no double bonds. All the bonds are single, and this makes them solid. Why is that? Because the double bond kind of introduces sort of a steep angle in the molecule, and this prevents the molecule from packing up in a very neat and ordered way, so that the molecule, the whole substance tends to be liquid. When all the bonds are single, you get a nice repetitive zigzag structure in the molecule. We are talking of very long chain, like 16, 18 atoms of carbon. And the regular shape allows molecule to pack neatly, getting closer to each other, and therefore have more interactions than being solid. So why would we want to break the double bonds and add hydrogen? If we do that, if we add hydrogen and we end up with this molecule that, respect to the one we started from, has 2 extra hydrogen, no double bonds and just single bonds, this would be solid, right? So we would get to this, that is a solid. Writing with the mouse is not really easy. And because we started from this, that this was a liquid. Why? What would be the interest in doing that? The interest is, this is a process that's done in the industry. It's called hydrogenation. So you start from a liquid fat and you get a solid fat that's called a hydrogenated fat. You might have heard this terminology. The reason you do that is because you get, basically you're starting from, let's say, palm oil, and you're getting margarine or Crisco. And that increases the life shelf because there is basically no water left, and is also a solid is much easier to package and transport. And this process started to be interesting at during World War I, where they had to deploy a lot of soldiers in Europe. They need to feed them. They needed to have something that was cheap and easy to transport to the troops. And so, in terms of fat component of the diet, they started to work on buying cheap vegetable oils and transform them into solid margarine and Crisco, basically. And that's how the whole Crisco business started. There are problems with that, and we may come to talk about it. But that's a different story. So let's stay on topic and let's talk about catalysts. So the reaction happens at high temperature, and it's much faster if you use a catalyst. Why? Because in order to create this new structure, you need to break the double bond. You need to break this double bond. And you need to break the bond between hydrogen and hydrogen, and then make a new bond between carbon and hydrogen, and another bond here. So the presence of a catalyst, in this case, the catalyst is these two substances, maybe liquid or maybe gas, depending on the molecular mass, but the catalyst is a solid piece of metal. Most catalysts are metallic. It's a metallic surface. Sometimes it could be as simple as iron, and that's the catalyst they use, for example, in the industrial process of production of ammonia. Some other times you may need a more expensive metal like platinum. But the thing is, both substances will be absorbed on the metal, so will somehow interact with the metal. This interaction with the metal causes the formation of a partial bond between the atoms and the metal, and that determines the breakage or the weakening of the pre-existing bond, hydrogen-hydrogen bond, and the second carbon-carbon bond. And also the proximity between the molecules make much easier for them to actually make a new bond. So through this process, it's facilitated the formation of the compound we are looking for. So it's a bit like a match.com of chemistry. The catalysts provide a platform that makes easier for the molecule to interact, and it requires less energy. Or sometimes and that would be an heterogeneous catalysis, because you have different phases. In this example, there is a catalyst, but it's a different type of interaction. Everything here is a gas, including the catalyst. So this is more is what we call a homogeneous catalysis. So the molecule, you may recognize this molecule. This is ozone. Ozone is can be a good guy or a bad guy. Is very desirable to have a lot of ozone in the troposphere, so in the very high level of the atmosphere. because it protects us from dangerous radiation that are coming from the sun, like gamma rays and the more short wavelength UV. And in the 80s, they start noticing that there was a depletion, like a lowering in the concentration of the ozone in the atmosphere, especially in certain areas. So there was what they call the ozone hole, and it was a major concern at the time. It was as concerning as, almost as concerning as global, the climate changes is now. And they realized that the reason it was depleted was that there is a normally there is a process of consuming ozone and then reforming it in the higher layer of the atmosphere. But there was compounds that were coming from these classes of compounds. So these are chlorofluorocarbons compounds. So these are compounds where there is a central atom of carbon, and then carbon makes 4 bonds, and so it could be connected to, for example, 1 chlorine and 3 fluorine and so forth. These are compounds that are used in refrigeration. So your fridge works by expanding and compressing a gas, and we will talk about that in thermodynamics. And the gas that's inside are these type of compounds. They are very useful because they are inert. The problem is that when you dispose, when the fridge is done and it's open, these compounds would evaporate and would go up in the atmosphere, and up in the atmosphere they would catalyze or make much faster the decomposition of ozone, so eventually reducing the total amount of ozone. Ozone, though, is something you don't want in the lower layer of the atmosphere. Is a pollutant, and it would cause damage to the respiratory system, it would damage plants, it would even increase the deterioration of rubber in tires. So it's good to have ozone in the upper atmosphere, not in the lower atmosphere. So the catalyst would be chlorine, that comes from the decomposition of these chlorofluorocarbon compounds, and it reacts with the ozone in the first step of the reaction, and then you're forming these compounds. This compound that does not appear in the total balance equation is used up here, right? So we have already seen those are intermediate. They get used up, produced in the first step, and then used up in the second step. Chlorine is a catalyst. It gets used up in the first step, so it's necessary to start the reaction. It gets used up and then is produced again. So also for chlorine, we can say that the total balance is 0, right? So if we put together those two reactions, we see that the chloro-oxygen compound that we have identified as an intermediate appears and then disappears, and so we can simplify, we can cancel out. Chlorine instead is there, gets used up and then reappears. So it kind of it's in a way it's similar because it gets cancelled out, but what's different is the sequence. For ClO, it's formed and then used up. Chlorine is used up and then formed, and this is what makes it a catalyst. So it's important to be able to identify them, right? So they both do not appear in the balance equation. The intermediate is generated earlier on and then consumed. A catalyst needs to be there because it is the trigger for the reaction to happen, but then is consumed, so the total amount is constant. That's why, if you remember, when we used manganese dioxide to trigger the decomposition of hydrogen peroxide in the lab, I told you to just use a tip of a spatula, that you didn't need a lot because it was not used up. So what have we learned so far? That we have learned that the rate of a reaction depends on the concentration of the reactant. In a way that's not linear, there is an exponent, And so depending on the value of that exponent, the effect of changing the reactant concentration can be more or less dramatic. The order, that is the exponent, depends on the mechanism, and to be determined we need an experiment. In particularly, when there are multiple steps, the critical one is the slow step, the rate limiting step. We learned that temperature will increase the rate constant any time, every single time. It does not make any difference if the reaction is exo or endothermic. The temperature will always increase the speed. And the molecules need to collide with sufficient energy and the correct orientation for the reaction to happen. So this equation that looks a bit scary is the Arrhenius equation, and it allows us to relate mathematically the temperature with the rate constant K. So we said that the temperature, when the temperature goes up, for every reaction, never mind if it's exothermic or endothermic, the rate constant is going to be bigger, and therefore the reaction is going to be faster. This is the mathematical equation that allows you to connect those two. So what do we have in that equation? We have E, that's the base of the natural logarithm. We have the activation energy. We have the gas constant. Now, for the gas constant, we are going to use the values that is the joules. So 8.314 joules per moles per Kelvin. Because we have the activation energy that's also given in joules. Actually, most of the time in the problems you have the activation energy in kilojoules, so you need to be careful to use the proper value. The temperature needs to be in Kelvin, and this whole chunk is kind of giving you a sort of a quantitative evaluation of what's the fraction of the collision that are actually useful. And then there is this pre-exponential factor. Let's use a different color. Pre-exponential factor. And that kind of gives you information about the orientation of the collision. But you don't have to worry too much about. Yeah, right? Because it looks pretty scary, but we are going to try to simplify it. And the equation that you actually need is going to be given in the cover of the test. So first of all, we can simplify by putting together everything that's before the exponential component of the equation, and just call it A, like the first letter in Arrhenius. So that's going to already to make it a little bit simpler. Then what we can do, we can transform it and with a logarithmic transformation. So we can take the logarithm of both sides. What is the exponent of E becomes a multiplication factor. Because you have a multiplication between A and E, in the logarithm domain that becomes sum, right? So you get that the logarithm of K is equal to this factor plus logarithm of A. So this kind of it's a way to linearize the equation, because if you plot on a graph the logarithm of K on the y-axis and the reciprocal of T of the temperature on the x-axis, you get a nice straight line with a negative slope. And the negative slope is going to be this. Right? So the negative slope is very interesting because there is an R that's a constant, so we know exactly what it is. So the slope allows us to evaluate the activation energy. That's how you determine experimentally the activation energy of the reaction. So what you need to do is basically perform the reaction at with the same concentration at different temperatures. Like, so we learn in the lab how to, or you will learn in the lab, the virtual lab, how to determine the rate law. Once you get the rate law, you can figure out K, and once you have K, you can perform the experiment keeping the concentration constant at different temperature, so you can figure out the value of K at different temperature. So if you have, let's say, 5 different experiments with 5 different temperatures and 5 different values of K, you could put them in a graph. You know that it's supposed to be on a linear, so you can put a trend line into it and determine activation energy through that. So is it true that an increase in temperature would always make the reaction faster? Keep in mind, so let's have a look at the equation here at the top. So keep in mind that what makes a reaction exothermic or endothermic, so that would be delta H, is not even here, so it wouldn't have any effect, right? So if you increase the temperature, this fraction, the exponent, because the temperature is at the denominator, this fraction is going to be a smaller number. So E elevated to a smaller negative number is going to be bigger. So K is going to be bigger. So the only really things you can change here is temperature. So the rest, the activation energy is what it is, unless you use a catalyst. R is a constant, so really there isn't much suspense. If you're increasing T, K is getting bigger. So the effect of the temperature, as we said, is to increase the K, and here you can see that we know that if we have a certain activation energy, when we increase the temperature, we are increasing the fraction of the molecule that have energy equal to activation energy or more. So in this case, it would be this gray area. So the fraction of molecule that can transform into products is getting bigger. So if we are in the business of making something and we want to make money out of it, and so we want to make it faster, we want to increase K. So if we want to make K bigger, we have two, let's say, options. One is to increase the temperature. Increasing the temperature will affect K. The other one is to provide a different path that has a lower activation energy, and this can be done by using a catalyst. So a more useful way to use the Arrhenius equation is this. It's like a two-point Arrhenius equation, and this is just derived algebraically from the other one, so I will show you in the next slide if you're curious how, but you don't have to do that because this equation is given as well. So both forms of the Arrhenius equation are given, so you can pick the one that you feel more useful, depending on the circumstances. So if you perform two experiments, just two experiments, two different temperatures, at T1 you would have a kinetic constant equal to K1, and then you increase the temperature to T2, and you would get a faster reaction, so K2 is going to be bigger than K1, and T2 is going to be bigger than T1. And then using this equation, you can solve for different variables. For example, if I give you both temperature and I give you both constant, I can ask you to calculate the activation energy. Or if I give you the activation energy and 3 of the other variable, like 1 of the K and 2 temperature, I can ask you to solve for the missing one, right? So we're going to see some examples. So this is to show you how you actually get to that, how you get to the 2 points equation. You calculate you start from your Arrhenius equation, and you calculate the logarithm of it, and then you do you write the equation twice for 2 different values of temperature, and then you calculate the difference between the two. So you go first equation minus the second one, and this way you get rid of logarithm of A, and that would be kind of hard to determine. And so you get the equation that I showed you before. But as I said, you don't have to worry too much about that because it's given in the front page of the exam or the cheat sheet that I'm going to give you online. So first example of a problem with Arrhenius. a reaction was observed at 2 different temperatures. So the fact that I'm saying at 2 different temperatures should immediately trigger in your mind that you want to use the 2-point equation. That you want to use this one. So you have the rate constant determined at 3 Celsius and then determined at 34 Celsius. You're given both temperature, you're given both constant. You need to calculate the activation energy. So your unknown is this. So here the possible, so basically it's a plug-and-chug situation. Where you can do an error, a mistake, is units, forgetting conversions, and messing up 1 and 2. So make sure you pair them correctly. So at 3 Celsius, that's T1 because it's the smallest temperature. You have the smallest, so let's do them in green, okay? So smallest K correspond to the lowest temperature, and then let's do it blue. The highest temperature correspond to the highest constant. So the problem with the units here is that you have the temperature in Celsius, so you need to transform into Kelvin. You need to remember that R is in joules. So in this case, you are calculating EA, so the result will come up in joules. It's a multiple choice. The likelihood is that the multiple choices are joules, are kilojoules. If the teacher is particularly evil that day, they will put one of the answers, like the number you would get if you forget to convert from kilojoules in joules, with the wrong units to see if they can trick you. Right? So for example, if it's a multiple choice, the correct answer is 45.9 kilojoules. If you just do the math and you plug in R as 8.314, the actual number you get out of the calculator is going to be 45,900, right? So if I'm particularly evil, I may put as one of the 4 choices, instead of 45.9 kilojoules, that's going to be there because it's the correct answer, I may also put 45,900 kilojoules. That's incorrect. But because you see the same number you see on the calculator, if you are a bit in a hurry, and you may just, you know, be too hasty and click the wrong answer. Okay. So this is a second example. We have a certain reaction, we are given the activation energy in kilojoules, and we have the 2 temperatures in Celsius, how much faster the reaction was. So first of all, let's fix all the units, right? So we know that is a 2-point reaction because we want to use the 2-point equation that we used before in the example before. We know that because we have 2 temperatures and 2 okay, so that's just the right way to approach it. First of all, let's fix all the units. Okay, so T1 needs to be in Kelvin, T2 in Kelvin, and activation energy needs to be transformed in joules because R is in joules. So you want a consistency between this and this. And now it's plug and chug. Now the problem is that you have EA. You have T2, you have T1, and you have 2 unknowns because you don't know K2, you don't know K1, and you need to know both to determine how much faster the reaction is. So it almost seems like you don't have enough information to solve the problem. But if you pay close attention, you may notice that it's not asking you to determine the absolute value of neither K1 or K2. What it's asking you is how much faster. So actually what it's asking you is how bigger is K2 respect to K1? So the unknown is not K2, is not K1, is K2 divided K1. So that should make easier. So basically you set this as X and you plug all the other number and you solve for x, and you get 6.27. So the reaction is about 6 times faster.